FPGAs are some of the coolest chips I've worked with. However, even with how incredibly versatile and powerful they can be, they don't get too much attention from the DIY crowd. The biggest project I've used one for is the Industrial Robot Controller. An FPGA handles all of the communication between the motor drives and the feedback encoders on the robot. I'm going to go into detail on how it all works later in the video, but first let's cover some of the basics. There's a lot to go over, so you might want to grab some snacks, but I promise you by the end, you'll also think FPGAs are really cool. Let's start with something more common, the humble microcontroller. These are in almost every product these days, even where they probably shouldn't be. Many of you are probably familiar with microcontrollers through Arduino. They make boards that use various different microcontrollers for people to mess around with. I have mostly switched over to using Nucleos, which are STM's line of dev boards for their chips, very similar to Arduino's. To use them, you write a program in the language of your choosing, usually C or C++, which is what Arduino uses. Compile it, then send it to the microcontroller where it starts running. FPGAs, however, are totally different. You configure hardware instead of software, meaning that by default, they can't run any programs, can't do really anything at all. They're just blank slates. But that also means they're so much more capable once you put in the work to configure them. When I hit the compile button for a microcontroller, the compiler converts my program into a long series of instructions and data. Then when I program the chip, the instructions and data get copied to the persistent memory called flash. That way, even after resetting or power cycling the microcontroller, it still retains the program. The CPU in the microcontroller then fetches an instruction from that memory. This instruction causes the CPU to do a specific action. For example, add numbers together or to move data around. So a program that adds two numbers together from memory might look like this. First, load the data for the first number from memory into register 0. You'll hear me talk about registers a lot throughout this video. All a register is an array of bits that you can read or write to. They're usually the inputs and outputs of logic functions. The numbers and data here are all also in binary, a bunch of ones and zeros, usually 32. So anytime we're moving data around or reading registers, we are moving groups of ones and zeros. In this case, the CPU has 13 32-bit registers available, and it just stored the first number in register 0. The next instruction would be to load the second number into register 1, then the final instruction would tell it to add registers 0 and 1 together and store the result in register 2. For actual program flow, there are branching instructions which tell the CPU to jump to a different instruction if certain conditions are met. This is how if statements and loops from the initial code work. The reason I'm going over all this is to point out that CPUs have a relatively small set of fixed capabilities when compared to the many different tasks they need to run. They complete them in small, simple parts, one at a time. Since they run instructions millions or billions of times per second, it's usually not much of an issue to do it all one step at a time. The CPU is made up of thousands of logic gates. All of the functions that can be run using the instructions are built out of the most basic logical elements, like AND gates and OR gates. These are baked into the physical structure of the chip, so there's no changing it. You can't upgrade to get newer instructions or fix a bug in the hardware if you find one. Once it's manufactured, you can't change it. However, with FPGAs, you can. I'll go over some examples of what this actually lets you do, including taking a closer look at how the FPGA works in my robot controller. Thanks to PCBWay for sponsoring this project. All of the custom boards in the controller were supplied by them, as well as the sheet metal enclosures for the motor drives. They also offer full assembly services where they will order and solder all of the parts onto your board, which is what I had done for the motor drives since I would have had to place hundreds of parts myself otherwise. To order, simply go to their website and select what service you want, then upload your manufacturing files and configure their options, then get an instant quote back from them. Use the link below to get a discount on your first order. Before I get to the examples, let's first take a look at how it's even possible to reconfigure the hardware in an FPGA. FPGA stands for Field Programmable Gate Array, with those gates being the same ones that we looked at earlier that made up the microcontroller CPU. Well, functionally the same, but an FPGA isn't just full of individual logic gates you can connect together. They're quite a bit smarter than that. All logic gates have truth tables that go along with them to describe how they work. They specify every possible input and output combination, meaning if you know the inputs, you can look at the table to find what the output would be. The FPGA I'm using has LUT6s in it, which are lookup tables with 6 inputs. They are basically a tiny block of memory that is programmed at startup, a specific output state for each of the 64 possible input states. By programming in what we want the truth table to look like, we can effectively make any type of logic gate, or even combinations of multiple gates for more complex operations, as long as there are 6 or less input signals. However, multiple LUTs will automatically be linked together to support as many inputs as needed. Those LUTs are organized into groups called configurable logic blocks, or CLBs. In my case, each block contains 8 LUTs, as well as 2 4-bit adders for doing math, and 16 flip-flops. Flip-flops are fundamental to how most logic is implemented. So far, the LUTs, logic gates, and adders are basically instant. When an input changes, the output follows soon after. The delays here are typically well under a nanosecond. However, once you combine lots of them together, the delays start to add up. Flip-flops are used to break these long chains and synchronize the logic with a clock signal. They are essentially one bit of memory. Whenever triggered by a clock signal, they store the input signal and begin outputting it. Basically, the output only ever changes when triggered by the clock. This allows signals to incrementally step through as the clock signal toggles. This type of logic is called synchronous since it is tied to the clock. The other type is called combinational logic and doesn't depend on a clock. The outputs change shortly after the inputs regardless of the clock signal. So how does breaking up those large chains help? To start, if a chain takes long enough, it might need more time than just one clock cycle, which means you either need to slow down the clock or break the logic into smaller steps. If you don't, you can end up sampling a signal right as it's changing. If a signal is feeding into a flip-flop that is triggered while the input is mid-transition, it can cause something called metastability. Sometimes it'll read the old value, sometimes the new value, and in the worst case, it can go into a weird in-between state for a brief moment before it finally settles. The worst part is this might only happen 1 in a million cycles, so it can make finding these issues really challenging. Any sort of uncertainty like this is terrible to plan for, so it's best to design logic so signals have plenty of time to settle before the clock edge. Luckily, the software to program FPGAs will check for this and throw errors if it finds any issues. However, there are still certain cases where issues can be missed, primarily when signals are crossing between different clocks or are not clocked at all like an external input. Another reason to break the logic into smaller segments is that it keeps the clock speed high. At first, you may think running logic in one clock cycle at 1 MHz is the same as running it in 10 cycles at 10 MHz, and this is partially true. It still takes just as long from when the data is input to get the result. The cool part with using the higher clock and sequential logic is it can be computing multiple results at once. You can input and output data on every cycle. There's still the 10 cycle delay, but the throughput is now 10 times what we could do at the lower clock speed. This method of breaking up logic into sequential steps is called pipelining. This is a common way to increase performance. Same latency, but 10 times the throughput. A similar method is used for moving data around. Much of the delay in FPGAs is not actually from the logic itself, but is from the connections between the CLBs I talked about earlier. There are usually thousands of CLBs in each FPGA, but you can get tiny cheap ones with only hundreds, or enormous ones with hundreds of thousands. The one I'm using has around 7,000. Most logic functions require more than one CLB, so there needs to be a way to connect them together. The CLBs are arranged in a large array, with wires passing between them vertically and horizontally. At the junctions where the wires cross over, there are configurable switches that can be programmed to change how the signals route through. The CLB signals are attached to those wires through even more configurable switches. By programming all of those switches, signals can be routed between various CLBs to build up very complicated functions. The downside is that every switch adds capacitance to the wires, which slows down how fast signals can pass through them. For this reason, not every wire has the option to connect at every junction. Some wires skip, say, every 5, meaning you only have the option to connect to it every 6 spaces. This results in fewer switches for the distance traveled and allows for routing signals further with less delay. Still, if you're routing fast signals very far, you might need flip-flops in the middle to break it up, like the logic pipelining I talked about earlier. With this setup here, pretty much any sort of logic can be built. You're only limited by the total number of available logic blocks and getting the signals where they need to go. However, many FPGAs include a couple additional resources to use, not just the CLBs. In my case, they are DSPs and BRAM, but different FPGAs may have different types or amounts of additional resources. Some may not have any at all besides the CLBs. DSP stands for Digital Signal Processing. They are simply dedicated math functions. We could 100% do math with enough of the CLBs, however, not only does that of course use them up, but is also comparatively slow when compared to the dedicated logic in a DSP block. DSP blocks are very fast and energy efficient, so it's best to use them where possible. Often this means designing algorithms that fit nicely within their capabilities so they can be fully utilized. My FPGA has 220 DSP48E1s in it. They are pretty complicated and have a lot of functionality, but they primarily are a 25 by 18-bit signed multiplier with a 48-bit accumulator. We are only working with integer or fixed point numbers here. Floating point math is a whole different beast to deal with. It can still be done in an FPGA, but it is almost always more efficient to find a way to implement your functions using fixed point numbers instead. So, the DSP block multiplies two numbers, then adds or subtracts them from another number. It also has functions like rounding, a pre-adder before the multiplier, and various add or subtract combinations and sources. They can be partially configured by surrounding logic, so they can do different operations without needing the FPGA to be completely reprogrammed. They are also designed in such a way that the output of one can directly link into the next without needing to go through the configurable grid of wires, allowing many blocks to be chained together with very little delay, perfect for high performance. Next is the BRAM, which stands for block RAM. These are dedicated chunks of memory spread out around the chip. You frequently need memory to run various functions. In many cases, you're only storing a few numbers, so it's easiest to implement that memory using the CLBs. However, if you're doing some operation that requires hundreds or thousands of numbers, you don't want to burn up all the CLBs as memory. So once again, there's a better dedicated option. My FPGA has 140 36 kilobit memory blocks, each of which can be configured for various widths and depths, meaning how many bits each number is and how many numbers can be stored. In this case, 1 wide by 36,000 deep to 72 wide by 512 deep. And of course, multiple can be chained together to get wider or deeper memory if needed. This BRAM is considered true dual port, which means you can read or write to it through two different ports at the same time, even with different clocks. This is useful for moving data between logic that might not be running at the same speed, or ensuring logic on one side can stay using the memory while new data is being added from the other side. And finally, the last main part of FPGAs that I'm going to go over are the I/O buffers. All of the signals we looked at so far are very weak and low power, not powerful enough to handle driving any external loads. So on the outside of the chip, there are a bunch of I/O buffers that are higher power, each connected to one of the physical pins on the chip. These are how we get signals in and out of the FPGA logic to the rest of the world. Once again, they are way more configurable than you might expect. They support a bunch of different voltages and I/O standards. Now, keep in mind, they're all still low-power digital signals, so only 1.2 to 3.3 volts, but they can handle many different types of connected devices, even supporting differential pairs with a built-in serializer, which allows sending and receiving data much faster than the internal clock frequency. In this case, up to 1.25 gigabit. They can also be set as bidirectional, so both inputs and outputs, which is what I use for the robot controller since it's the most versatile. However, these signals don't stay bidirectional in the FPGA. The buffer takes in an output and output enable signal and sends back an input signal. You can't read the external signal properly if you're trying to output, so you need to disable the output before trying to read it. Now that you know what's inside an FPGA, let's move on to how they're programmed. Thankfully, the tools to configure them are awfully smart. We don't really need to worry about how the wires get connected or specifying the raw logic gates ourselves. Instead, we use something called an HDL, or a hardware description language. This is where we write logic modules, the FPGA equivalent of writing a program in C++ or whatever other language. There are two main HDLs to choose from, Verilog or VHDL. However, for the robot controller, I used an interesting open source alternative called Amaranth HDL. It ends up all converting to Verilog eventually, but the cool part is that it starts out as being Python based. So it's super easy to automate if you're already familiar with Python like I was. Switching to an HDL from a normal software language like C++ or Python is a really weird experience. Remember, we're defining hardware now, not instructions, so there's no sequential flow from top to bottom like usual. Everything happens all at once. Amaranth has a web playground you can mess with if you like, and it's super easy to set up and run yourself if you're already somewhat familiar with Python. Let's have a look at one of the simplest things you can make in an FPGA: a counter. This is the example from the website demo. At the very top, we have all the imports to use Amaranth. Then we create some signals: en, which will enable the counter when on, and a count, which will be the counter value. The 4 there is specifying how many bits the signal is, leaving it blank defaults to just 1 bit. This is also where we have the option to specify signed or unsigned, and what the starting value should be. By default, they're all unsigned and start at 0. These signals are similar to variables in other languages, however, not exactly the same. In software, when we create a variable, it's a location in memory that holds some data, so when we use it, we are reading from or writing to that memory. However, for signals, all they are is a group of wires. 4 bits means 4 wires. To connect those wires to logic, we create a module. This is where we add all the logic functions we want to use. Amaranth requires this weird syntax to specify if statements and such. Python doesn't let you overwrite the existing if statements, so this is how those types of statements need to be added to the module. This is saying, if the enable signal is active, then run everything in here. Synchronous logic is linked to clock signals, or clock domains as they're called. If we want our counter to increment on every clock cycle, then we want to add it to that clock domain. The sync domain here is the default synchronous clock. So this line is saying, add the logic to make count equal to count plus 1, and run it on each clock cycle. And since we're still in that if statement, only do it if the enable signal is set. The next line is adding logic to the combinational domain, meaning it happens instantly, no waiting for a clock signal. So the moment count is no longer less than 5, that comparison is now false, and the enable signal is set to 0, stopping the counter. So we are expecting the counter to go up to 5 and stop. Now, we could go through the whole process of loading this onto the FPGA and testing it, but thankfully there's a much simpler way to test the logic. Amaranth has a built-in simulator. Now, this isn't simulating the CLBs or anything from the actual FPGA, just the higher level logic we previously defined. In fact, Amaranth doesn't need to know anything about our specific FPGA for this. The simulation is done using test benches. We use this line to increment 1 clock cycle, and also have read and write access to all of the signals we defined. I use this to test the input signals I captured from my robot encoders, so I can make sure my decoder logic works properly without even needing the FPGA. Here we are going to loop 10 times, each time incrementing 1 clock cycle and then printing the counter value. The rest is setting up the simulator and running it. This is also where we can set the clock period, the time between each clock cycle. This doesn't actually affect how the simulator works at all, but just changes the time steps in the output waveforms. What waveforms, you may wonder? Well, the simulator saves the values of every signal at every time step, so you can view them like on an oscilloscope. Here we can see count being incremented on the rising edge of each clock signal. Then once we hit 5, the enable signal goes to 0 and we stop counting. If we look back at the code, I'd like to show you the first thing that really tripped me up when learning to use FPGAs. Something like this. I added count 2 and am setting it equal to count on each clock cycle. Coming from normal programming, you would be inclined to think that it'll take count and add 1 to it, then set count 2 equal to count. So they should always equal the same thing. Yet when we look at the waveforms, count 2 is always 1 behind. I have since started thinking about the logic as running from left to right rather than top to bottom. Both of those lines run at the exact same time, so the count value that count 2 gets is the value it was before the addition logic was run. Now, the left to right thing is only partially true, since if I were to put some other synchronous logic outside of the if statement so it runs every cycle, it is indeed more left, but it still runs at the same time as everything else in the synchronous domain. The left to right thing's just another way to think about it that might help you get started easier. It helped me at least. So now that we have all of our logic, we can begin the long process of getting it onto the FPGA. All of the logic from Amaranth is saved to a Verilog file, and I can import it into Vivado. Vivado is the toolchain from AMD, the manufacturer of my FPGA. and it is interesting to say the least. An absolute joy to work with. This isn't going to be a tutorial on setting up a project. I barely managed to get mine working, so I'll just go over the highlights. Logic blocks are organized in a block diagram, showing the connections between all of them and allowing for some automated configuration. This graphical layout isn't required, but it can help make certain projects easier to visualize. These blocks are often called IP cores. Tons of them are included for free and implement various functions for you to use. That way you don't need to write every function yourself. Most of them have interfaces to configure them for your specific uses as well. There are also many that are not free, which can cost thousands of dollars and come with specific licensing restrictions and whatnot. Here I have the layout that the robot controller is using. You don't need to have this much stuff to get a basic project going, however, it's a lot easier for me to reuse this setup to explain everything than starting new. For now, you can ignore everything except this block here. This is the robot controller logic that Amaranth has generated. It has a bunch of input and output signals. The ones we're interested in here for testing are the input and output signals to the card slots. Each slot has 22 signals run to it. Now, let's come up with some simple logic we can connect up to those pins to actually do something. The counter we looked at before only counts up once, so it doesn't really have any good signals we can look at. Instead, how about we make a PWM signal? So, a pulse at a constant frequency, but with configurable width. Many of you are probably familiar with this if you've ever used an Arduino to dim an LED before. For this module, there's some extra stuff that is needed for the robot controller to function. We don't need it to generate the PWM signal, but I'll still explain it later. The main input and output signals are defined up here now. They are what signals are available to the external logic. In this case, all we need is the PWM output signal. In the module, we have a counter signal as well as a duty cycle signal. This is what we will use to set how long the output is on. The code here calculates how many clock cycles per PWM period are needed to get the desired frequency. The range function can be used to automatically determine the signal size needed to store that size number, rather than us needing to specify the number of bits manually each time. Then we have the synchronous logic that makes the counter increment each cycle, as well as reset back to 0 once it hits the correct number of cycles. Next is the combinational logic that turns on the output when the counter is less than the duty cycle value. So, the larger the duty cycle is, the longer the output will stay on. And that's it. We can simulate it again and see that it all looks correct. Next is tying it into the rest of the controller. It needs to be added to the list of nodes. These are all the customizable modules that will be included in the robot controller. Then, it needs to have its output signal attached to a physical pin. This will eventually be done through some large selector that could change it at runtime when configuring the controller, but for now it's just done manually. Then we're good to go. This Python program generates everything needed to configure the FPGA. It runs Vivado automatically, which is what you see it doing in the terminal. This takes a few minutes to complete since it's doing some pretty intense work behind the scenes. Once it's done, we can see the results. The summary shows resource usage and some stats, like estimated power usage and how bad my worst signal timing is. If this number goes negative, that means somewhere signal delay is too long to complete within the required clock cycle. I'm fine at around 2 nanoseconds of leeway. When I run this Python program, the first thing that happens is the Amaranth logic gets turned into Verilog. Then Vivado turns that into generic logic functions. In the case of the PWM module, the counter and its control if-else statements turn into this. Registers to hold the count value, as well as an equal comparison to check whether the counter has reached the target, and an adder to increment the counter. That equal comparison controls this mux, or multiplexer, to select whether it should set the counter back to 0, or to the incremented value from the adder. Then there's a final less than comparison to check if the output should be on or not. That binary value it's comparing with equates to what the duty cycle signal was set to in our original code. This is the last time we'll be able to somewhat easily follow much of a logic flow. The next step builds these generic logic functions using the LUTs and everything else we talked about before, what is actually inside the FPGA. Here it turns into a bit of a mess. Luckily, you usually won't need to be following logic through these entire schematics. Mostly just when you want to make sure certain functions are being used, like the DSPs, or if you're debugging issues. Speaking of debugging issues, just like compilers for software, there is a ton of optimization that goes on. For example, if I make the PWM duty cycle 0, so it should just be off all the time, and rerun everything, the elaboration step still produces the full counter and compare logic, but the synthesis step completely removes the entire module. There isn't even a spot for it anymore. Then the output pin to the I/O buffer just gets tied straight to 0. So if you notice signals being tied high or low when you didn't explicitly specify, it was probably optimization that concluded that was the only possible state for them. The next step in configuring the FPGA is placing those logic elements into it. After that, we can see exactly how the FPGA will be configured. Vivado visualizes every single signal and logic element available. What you're looking at is a representation of the actual silicon die in the chip. The PWM logic is tucked away right in here. The rest of this is other stuff we'll get to later. You can see the individual CLBs and wires connecting everything, even the big interconnect switches that route those wires around. The output signal from the PWM logic shoots across the whole chip up to its I/O buffer, which sends it out to the real world. The final step is writing the configuration to a bitstream file. This is the final binary data that is loaded into the FPGA. FPGAs, however, do not have non-volatile memory like the flash on a microcontroller. FPGA configurations get erased when power is lost. We obviously don't want to hook up a programmer every time, so usually there is some external memory that the configuration is saved in and loaded from, or some other device that loads it on. There are some special FPGAs that do have flash to save the configuration, but they're usually for much more specialized applications. After the configuration is loaded, if I look at that pin on the scope, it does indeed make a signal that matches the simulation. So at this point you might be thinking, wow, that was an awful lot of work just to blink a pin really fast. And indeed it is. It took me weeks to blink an LED the first time, and let me tell you, the difference between wow, it's working and I just spent 3 weeks to blink an LED really makes you think. Luckily, a lot of that time is spent in the initial setup. Once that's worked out, adding new functions is so much faster and easier. Before I get into the rest of the robot controller logic, let's take a moment to talk about when and why you might want to use an FPGA over something like a microcontroller. How about I try implementing our same PWM generator in software on a microcontroller and see how it does? That's pretty straightforward. Turn the pin on, wait 50 microseconds, turn it off, wait again, and repeat. Now, if we hook it up to the scope, all seems well to start, but if I zoom way in to the end of the pulses, it's clear something is wrong. They aren't very consistent at all. They're mostly within about 70 nanoseconds, but sometimes they're all the way out at 500 nanoseconds apart. This timing variation is called jitter. The FPGA signal has basically none in comparison. This is pretty strange since the microcontroller code is supposed to do the exact same thing every cycle. Even if there are slight delays in turning the pin on or off, they should at least be consistent, right? Well, they aren't. Most of today's CPUs are not 100% timing deterministic anymore. There is no guarantee that each line will take a consistent number of clock cycles to complete, let alone an exact number you could factor in to get precise timing. This is due to a few different reasons, mostly that processors try their best to optimize for speed. So they usually don't actually load data straight from flash since it's slow. It can't be read at the same speed the CPU can run at. Instead, there's a little bit of high-speed memory in between called cache. That way, the required data can be loaded into that from flash, then into the CPU much faster. Ideally, all of the data needed would be loaded into cache so the CPU would never need to wait for flash. But the cache is only so big, so it eventually needs to have the data swapped out as the program moves along. Cache does boost performance, but at the cost of a bit of uncertainty in how long it'll take the CPU to fetch some more data, depending on if it's available in cache or if it'll need to get it from flash. Another source of uncertainty comes from the processor itself trying to plan ahead and start multiple instructions at once, boosting performance overall, but sometimes causing an extra small delay. And then there are the data bus delays. These are how the CPU tells the pins to turn on or off. Depending on how much data is being sent through them and how fast they can run, they can also introduce variable delays. There's a couple ways to improve this jitter, first being to not use these helpful functions to control the pins that do a ton of other stuff in the background. Instead, we can write straight to the registers that control the pins. This brings the jitter down to only 40 nanoseconds. We can also even disable that memory cache, but in this case it actually makes it worse. Now, I'm sure some of you are already typing away in the comments, use a timer. And yes, this is exactly where you'd want to use a timer. The manufacturers of most microcontrollers know that generating PWM signals is a pretty common thing to do, So instead of needing to burn up CPU effort to simply toggle a pin and wait, they include timers. These are basically fancy versions of the PWM generator we made in the FPGA, just way more configurable. They are connected to the CPU through a memory bus just like the I/O pins, but with the timer having full control over the pin instead of the CPU. So there is essentially zero jitter. And once the timer is configured and running, the CPU doesn't need to do anything to keep it running. So not only is it way more consistent than the CPU, but it also saves processing effort that the CPU can now spend on other tasks. Things like that timer are called peripherals. There are usually quite a few of them available. They typically handle various signals being sent or received from the physical pins, greatly reducing the load on the CPU. Some microcontrollers even have modules called DMA controllers. They can be programmed to transfer data directly between a peripheral and the main memory. That way, if for example, the microcontroller is receiving a bunch of data through some communication peripheral, that data can be saved straight to memory automatically. No need for the CPU to be stuck there watching the peripheral, waiting for the next data byte to be ready to save. Most of the time, you can find a microcontroller with the right peripherals and extra functions to do whatever you need. FPGAs mainly come in where you either need a ton of signals, like running phased arrays, very tight timing where you need to input and output data with very low latency and jitter, high throughput, like combining video streams or dealing with high-speed networking, or lots of versatility to support future changes and unknowns. FPGAs aren't without downsides though. They are expensive, complex to design boards around, and more complex to program than microcontrollers. But in some cases, those downsides are worth it. This is why FPGAs aren't very common in the hobby DIY world. They are often used in aerospace and defense or medical devices, usually stuff that's way more expensive. However, they aren't completely unheard of when it comes to hobby stuff. A popular use for them is retro game emulation, where they can emulate the hardware from whatever game console they want. Can't be any more versatile than being able to build any type of CPU and peripherals you want into the same chip. FPGAs also typically are not good for heavily branching functions like CPUs are. They like relatively small functions with a limited number of inputs and output cases. You'd never want to do something like build a website out of logic. There's simply way too much going on. Instead, you'd just use a normal processor. Let's finally have a look at how my robot controller works. If you haven't seen my previous video on this, it goes into much more detail and is definitely worth a watch if you stayed this far through this video. But to sum it up, old industrial robots get thrown out all the time, so they're pretty cheap. However, the old controllers are either hard to use, hard to fix, or both. So I made this system of motor drives and other boards to completely replace the original controllers, and FPGA being at the core of all of it. I've been calling this an FPGA the whole video, but there's a bit more to it. It's actually a ZYNQ 7020, which is a system on chip. Remember that device diagram that showed all the logic elements? Well, there are actually two entire CPUs stuck in there. Those green paths are hundreds of connections between them and the rest of the FPGA. This chip is essentially set up like a microcontroller with the ability to run software on the CPUs, but instead of having fixed peripherals connected to specific pins, I can make any peripheral I want and connect it to any pin. This also isn't limited to logic talking to external pins. Another common use is making hardware accelerators that the CPUs can use to speed up their own tasks, kind of like how GPUs speed up graphics processing. This makes them unrivaled in versatility. You can get the best of both worlds, the ability to run software and the option to configure specialized logic, tightly integrated together. The processing system is referred to as the PS side and the programmable logic as the PL side. If we look at a diagram for the ZYNQ, there is quite a bit more going on than the small microcontroller. This whole section at the bottom is the FPGA. The block here are the two CPUs running at around 600 MHz, with even more cache like I mentioned before to help boost performance. The CPUs are Cortex A9s as opposed to the little Cortex M4 in the microcontroller. This means they're application processors. They have way more fancy optimization for higher performance than the microcontroller does. Usually they're running a full operating system instead of a single bare metal program like the microcontroller. They also have these things called neon engines, which can do a bunch of math operations all at once instead of one at a time like the little microcontroller, also greatly improving performance. There are also still fixed peripherals like the microcontroller had. In this case, they are pretty much all for communication, like Ethernet and USB, no PWM or anything. One of the big differences from the microcontroller is there is no flash here to store your program. Instead, it requires external memory to be connected, like an SD card. It also now supports external RAM, so it can have up to a gigabyte of DDR3 instead of a couple hundred kilobytes of SRAM. One whole gigabyte may not sound like a lot, but the controller is currently using only a small fraction of that. Efficient programs make all the difference. I'm just trying to run a robot, not open Chrome or anything. So how do I actually transfer data between the processors and the FPGA? Primarily through AXI ports. That's what all of those general purpose and high performance ports are below. These are like the buses in the microcontroller that connect the peripherals to the CPU. I used one of the 64-bit high performance ports to connect to the on-chip memory, or OCM. This is a small chunk of memory that is quickly accessible by the processors. It is also dual ported like the BRAM in the FPGA. So both the CPUs and my logic can have direct access to it. And it's super fast, up to 1.2 gigabytes a second. There are also a few interrupt signals sent from the programmable logic that tell the CPUs when the on-chip memory is updated and ready to use. The FPGA layout looks like this. The on-chip memory is the only thing here that the CPUs can access. There are 5 sections in it. 2 little 64-bit areas for control data to and from the programmable logic, 2 larger 4 kilobyte areas for actual data to be moved back and forth, and then a final 2 kilobyte instruction area. In the FPGA, there are only 3 sections of BRAM, 2 for the large 4 kilobyte data areas and 1 for the instructions. The control data simply gets used or generated directly from logic, no need to store it in memory. The AXI controller's job is to copy the instructions and data from the on-chip memory to BRAM and copy back other data from the BRAM to the on-chip memory. From there, the DMA controller shuffles data between all of the different nodes in the FPGA based on those instructions. There are 4 instructions, and they are about as simple as they come. End, which signifies to stop running instructions, no-op, which means do nothing, copy, which moves data between a specified source and destination, and wait, which waits a specific number of clock cycles. What I want to accomplish is transferring data between the main memory and any of the additional nodes, as well as directly between any of those nodes. It needs to be fast, efficient, and most importantly, deterministic. No timing jitter or uncertainty about the order the data will arrive. So instead of a bus like the microcontroller had, where the data always needs to go to or from the CPU, I want something that doesn't require moving data to a central point every time. Remember, having long logic chains that need to connect to a bunch of stuff end up needing to run slower. Shorter chains mean faster data transfer. To have the shortest chains possible, there isn't a big branching bus that connects to every node. Instead, they are connected in sequence to form a loop. Each command that gets sent along the loop looks like this. A source and destination node, source and destination memory address for the data inside of each node, the data itself, and flag bits that signify if the data has been read from the source and written to the destination. When a copy instruction is read, the DMA controller creates a command and adds it to the loop, specifying where to get the data and where to put it. As the command steps around, each node checks if it's the correct one that the command is trying to read or write to. If it is, then the node reads from or writes to its internal memory and updates the command data in flags. So data is being picked up and dropped off as those commands move around the loop. This is cool since a new command can be added every clock cycle, each moving 32 bits of data, and since it's running at 100 MHz, it does 100 million transfers per second. However, there's a fundamental issue with this layout. What happens if the node I want to write to is before the one I need to read from? In that case, the command just continues on around the loop until it reaches its destination. This does mean the controller can't send a new command while that existing one is passing through, which effectively halves the transfer throughput to only 50 million per second. Honestly, I might have spent a bit more time and effort than needed trying to optimize this part, because the current robot controller is using a whopping 0.2% of the available transfers. Oh well, at least it's living up to the channel name. This setup guarantees consistent timing since nothing can introduce a variable delay. Each node gets a set number of clock cycles to read or write the data, no waiting until they are ready or anything. This means the controller knows exactly when data is read from or written to each node down to a few nanoseconds. The transfer speed also isn't impacted by how many nodes there are. The logic currently supports up to 255 nodes. All that the number of nodes affects is the maximum transfer latency, not the actual throughput. Now let's look at what all nodes are running the robot. There are only 7. The first 2 control the serial cards plugged into the controller, stuff like configuring each port for RS422 or 485, and turning on and off the LEDs. Then there is the encoder interface. This is one of the best conveniences of having an FPGA. Since robot manufacturers love making up their own special protocols to communicate with their motor encoders, sometimes they are a pain to use with normal microcontrollers. Being able to make dedicated interface nodes for each type means that as long as they use RS485 or 422 twisted pairs, I can pretty much guarantee that the controller can use them, given enough time figuring out how to implement the protocol. I can also have as many interfaces as I want just by changing a number. No problem to have more motors than the 6 on the robot. The rest of the nodes are all for communicating with my own devices, like the servo drives, 3D mouse, and e-stop board. They are all 12.5 megabit serial. For now, none of the control loops are running in the FPGA, but they totally could be. The main update frequency is only 1 kHz. That's how often the FPGA memory gets synchronized with the on-chip memory. However, that doesn't mean that it can only read the encoders and update the servo drives once per cycle. Those commands can repeat, so it'd be perfectly fine to read the encoders 10 times in each cycle and add a PID loop node to run the control loops in the FPGA way faster than in software. I haven't done this yet since doing software only ended up working fine so far, but it's still an option for even better performance. Before I move on to the software side, let's look closer at one of those nodes in the FPGA. This BRAM stuff I skipped over in the PWM example now hopefully makes a bit more sense. These are the signals to read and write data from the DMA controller commands. But that isn't the main thing. A big reason I made many of the design choices I did when making this controller is for ease of configuration. It may not seem like it, but mostly everything can eventually be simplified down into a single config file to generate an FPGA configuration that can immediately be used. Much of ensuring configuration is easy is having a good way to specify and keep track of each memory address and what it's used for in every one of those nodes in the FPGA. So I made this register map generator. It helps make it so the software above all of this can easily access each node. Every register that I want to have available gets added, and it has its name, read-write permissions, type, size, and description set, just like how the peripheral registers in microcontrollers are documented. It even supports packing multiple smaller values into a single register, along with groups of registers, which is how a single node handles multiple instances of something, like the serial interfaces that connect to multiple devices. When the map is generated, it places all of those registers into the available memory space and passes the configuration up the chain. That way, when the FPGA configuration file is generated, it also makes a file that shows the layout of everything in the FPGA, including the names and types of every available register. Now that we finally have the FPGA configuration and register map files, let's move on to the software side. The processors are running Linux with some adjustments to help with real-time performance. The first thing that's done when the controller program starts is loading all of the configuration files. This includes the FPGA configuration and register map files we just looked at, an instruction file that tells the DMA controller in the FPGA where and when to move data to, and then finally node configuration files, for both the FPGA nodes and also software nodes that I haven't talked about yet. After the bitstream is sent to the FPGA, the software uses the register map file to load in all the drivers needed to run the nodes in the FPGA. That's where all of those register names and descriptions get used, and why we had to specify the driver type when making the modules. Those software drivers not only run the low-level controls needed to use the FPGA nodes, but also specify which basic instructions are needed to get them functioning. That way, I only need to worry about adding in custom additional instructions, not which ones are needed just for basic functionality. The FPGA node config file is used to set basic settings on the nodes, like which serial ports are enabled or what the baud rate is. It is also used to determine if any other default instructions are needed, like if some additional functionality is enabled that requires more data to be transferred. Then all of those default instructions, as well as any additional custom ones, are converted into the raw binary commands that the DMA controller can use, and sent to the on-chip memory. Once all of the FPGA stuff is set up, next up is the glorious node core configuration. This code is what turns all the fancy graphical nodes and wires connected together into actual real-time logic. In the last video, I got a lot of comments asking about what software I used to do this programming in, and it was made custom specifically for this project by someone on my Discord server. It ends up creating a file that specifies all the nodes and their connections that the controller can then load in and run. I think this setup is really cool and pretty easy to use. So much better than simple ladder logic or the complex text-based HOW files that Linux CNC uses. It is broken into node networks, which are large groups of nodes that are run one at a time. They run in sequence and can be enabled and disabled through logic, kinda like how ladder logic works. Then, in each network, the nodes are run one at a time starting from the inputs. The sequence is calculated automatically, unlike Linux CNC's setup where you manually set the order of each node. It also detects if you try feeding a node back into itself, as this would cause an infinite loop of trying to run the node to get the most up-to-date output. A one-cycle delay node must be added to break the cycle. It's not perfect, but good enough for now to mess around. In theory, live updates are supported, so I could adjust the nodes and connections in real time without needing to restart the controller, but I haven't tried any of that yet. For those curious how these run under the hood, it's basically exactly the same as Linux CNC HAL modules. The nodes are all C++ functions that get called in a sequence, with the wires connecting them being data pointers to where the node's input should come from. This way it's super fast and efficient to run, yet still easy to reconfigure at runtime. No recompiling needed to make any changes. Every update cycle, data is synced between these software nodes and the memory in the FPGA that the hardware nodes use, all together running the robot. With the software nodes being configurable at runtime super easily, and the FPGA having a completely automated build system and easy configuration settings, the controller can be reconfigured for a wide variety of different robots and machines. Different brands, different numbers of motors, even totally different machine setups. The goal is a controller that I can use to run basically any sort of old machine I come across, or even any new projects I want to make in the future. Once the bugs are worked out, having something as capable as this is going to let me get a lot more projects working way faster than I currently can. If you want to see more of this project and getting it used to make more cool stuff, be sure to like and subscribe. Thanks for watching.